Hello everyone, I am Amalu Sajir. I am here to introduce you to the topic Reservoir Sedimentation and Control. The topics we are going to cover in this presentation are reservoir sedimentation, some related terms, calculation of life of reservoir, trap efficiency of a reservoir, and finally reservoir sedimentation control. What is reservoir sedimentation? All the rivers carry a certain amount of silt eroded from the catchment area during heavy rains. This gradual accumulation of the incoming sediment load from a river in the reservoir of a dam is called reservoir sedimentation. Flow velocity of water reduces when it reaches the reservoir, so the sediment settles, thus reducing the space for water storage, which results in reduction of efficiency of the dam. It also ruins turbines in hydroelectric plants, causes aberration of spillways and outlets, reduction in surface area which can instead be used for recreation purposes. We also included a picture in this slide which shows flux of nitrogen, phosphorus and suspended sediment from the Susquehanna River basin, which is a clear indication of reservoir sedimentation. The extent of erosion and hence the silt load in the stream depends upon four factors: nature of soil of the catchment area, topography of catchment area, intensity of rainfall, and vegetation cover. Coming to our first factor, nature of soil of the catchment area. It is an important factor. If the soil is soft, there is always a possibility of sheet erosion, which contribute in more silt. The tributaries collecting water of the catchment area containing hard soil carry lesser silt. Now our second factor, topography of catchment area. Steep slopes gives rise to high velocities and erode the surface soil easily. Obviously, gentle slopes low velocity and causes less erosion. Third factor is intensity of rainfall. Similar to our previous factor, higher intensity of rainfall causes greater runoff and more erosion, while lower intensity causes lesser runoff, resulting in less erosion. Fourth factor is vegetation cover. If the catchment area has sufficient vegetation cover, the higher velocities are checked and erosion is very much reduced. Area having poor or practically no vegetal cover are productive of more silt. The rivers or tributaries passing through such areas carry more silt load with it, causing quick silting of the reservoir. Types of sediment loads. The sediment transported by the river can be divided into two heads: A. Bed load and B. Suspended load. The bed load is dragged along the bed of the stream. The suspended load is kept in suspension because of the vertical component of the eddies formed due to friction of flowing water against the bed. The bed load is generally much smaller, about 10 to 15% of the suspended load. When the stream approaches the reservoir, the velocity is very much reduced. Due to this reduction, the coarser particles settle in the head reaches of the reservoir, while the finer particles are kept in suspension for sufficient time till they settle just to the upstream side of the dam. It's clearly shown in our figure. Some fine particles may pass through turbines or spillways.
Hi, I'm Afzal. I'm introducing some related terms regarding reservoir sedimentation and control. The first one is sediment load measurement. For both practical purposes and field research, the sediment load of river is usually divided into finer suspended load and a coarse bed load. A range of instruments can be used depending on the method of sediment transport. The measurement of bed load can be made using fixed portable traps and samplers and tagging methods and electronic detection systems. Suspended sediment load is usually measured with both manual and automatic samplers. Continuous measurements are made possible using turgidity as a surrogate measurement of suspended sediment concentration. An advantage in the use of a manual and automatic sampler is to provide samples which can be subjected to further analysis for example, analysis of particle size distribution, chemistry, etc. One of the opportunities this can provide is to identify upcatchment sediment sources, gullies, and sheet rails, and surface erosion under different land uses. Um, the second one is density current. Density current is any current on either a liquid or a gas is kept on motion by the force of gravity acting on the difference in density. A density difference can exist between two fluids because of the difference in temperature, salinity, or concentration of suspended sediment. The density current is nature are exemplified by those current that flows along the bottom of the ocean or lakes. Such subaqueous current occurs because of some of the water in ocean or lake is colder or saltier or contains more suspended sediments and thus denser than the surrounding waters. As a consequence, it sinks and flows along the bottom under the effect of gravity. The difference in density, moreover, slows down the mixing of the current with the overlying waters, enabling it to maintain a relatively long distance. Density current are considerable practical importance. For example, the deposition of sediment from turbidity current, that is density current, in which the density difference is caused by the suspended sediment in lakes, may result in rapid decrease in the reservoir capacity. The rate of silting in case of reservoir can be reduced of the density current are vented by the proper location and operations of outlet and sluice gauges. Life of reservoirs. The ultimate density of reservoir is to be filled with silts deposits. To allow for silting, a certain percentage of total storage is usually left unutilized and is called dead storage. However, as time passes on, more and more silting takes place, and the
trap efficiency. It is defined as the percentage of total inflowing sediment that is retained on the reservoir. Trap efficiency is equal to sediments deposited in the reservoir by total sediments into 100. It is important when determining the annual sedimentation rate of the reservoir. It is found to be the function of capacity inflow ratio. Factors affecting trap efficiency. There are two factors, and they are hydraulic factors and sediment factors. Hydraulic factors are related to the structure and design of reservoir, and they are ratio of storage capacity to inflow rate, reservoir shape, type of outlets, and reservoir operations. Sediment factors. They are related to sedimental load getting deposited in the reservoir, and they are particle size distribution of inflowing sediment load. That is, coarser aggregates get settled faster than the finer aggregates. And second one is particle shape, and third one is behavior of fine sediments under temperature, concentration, turbulence, and water chemical composition. Based on the data taken from the existing reservoir, a graph is plotted between trap efficiency and capacity inflow ratio. From the graph, we can say that trap efficiency increases due to the increase in capacity inflow ratio. Therefore, rate of silting is higher at the initial stage than decreases as silting takes place. Hence, we can say that complete filling of reservoir with silt may take a long time. Thank you.
Hello, I'm Sri Lakshmi. Let us learn about calculation of life of a reservoir. So I hope that by reaching this far in the presentation, you might already know that life of a reservoir depends on sedimentation, which in turn depends on various other factors such as slope of the area, vegetation cover of the area, the type of soil that is present there, and all that. You might also know that life of a reservoir is usually terminated when the capacity reduces to 20% of its design capacity. Or in other words, you can say that when 80% of the design capacity is filled by sediments, we say that life of a reservoir has come to an end. That is, it has reached the end of its useful life. So let us look at how to calculate life of a reservoir. To calculate useful life of a reservoir, I have listed out a procedure which can be easily understood if you have a grasp of the concept. So initially there will be some inputs that will be given to us. That is, there will be inputs that tell us how much sediment is coming, how much inflow is coming, what capacity it is having, and what is the relationship between capacity inflow ratio and trap efficiency. So the first step will be to divide the total capacity into any suitable interval, say 10%. Calculate inflow ratio and trap efficiency for the reduced capacity. So why are we dividing this total capacity into sub-intervals? Because at different capacities, there will be different capacity inflow ratio, and in turn, there will be different trap efficiency. For example, initially, lot of the sediments that is coming will be trapped, but as capacity reduces, the amount of sediment that gets deposited also reduces. So let's say we calculate it for a 10% of the total capacity. So for this 10% capacity, find the average trap efficiency by taking the average of trap efficiencies found in 1 and 2. So there will be trap efficiency of total capacity, and then there will be trap efficiency of total capacity minus 10%. So what do we do? For the range that is from 100 to 90, we find average trap efficiency. That will be the trap efficiency of that range. Then we multiply the average trap efficiency by total annual sediment to find out what amount of sediment will be deposited. Then what do? We divide the volume interval by the sediment deposited determined in step 4 to determine the number of years to fill this volume interval by 10% capacity. So in this step, we'll understand how much sediment is deposited in a year, and we are taking 10% capacity. So to fill that 10% volume, how much years it will take? How many years it will take? That's what we find in step 4. So then we decrease the value by 10 again and again till 20% of the total capacity is reached. At that time, we can say the life of a reservoir has come to an end. So we add all these years to find the life of a reservoir. So let us look at a question. It will be more clear then. It is a previous university question. So as I said, we are given information about initial capacity, that is it can carry 50 million cubic meters, and then there is the average inflow rate, that is how much volume of water and sediments and whatnot is coming to the reservoir, that is 50 million cubic meters of stuff is coming to a reservoir. Then there is annual sediment flow, that is even in the inflow there will be sediments. So how much sediments are coming each year, that will be given as 300,000 tons. The other values are 50 cubic meters and 50 million cubic meters, both are 50 million cubic meters. Then the annual sediment inflow is expressed in tons, which can be related to kilogram, but we need all of this in a similar unit. So to convert it into volume, the density of the sediment is also given. Then what else is given? A relation between capacity inflow and trap efficiency is given. Trap efficiency for different capacity inflow is given. So as you can see, at high capacity, that is at full capacity, 97.7% of the sediments will be deposited. But as capacity decreases, I'm saying capacity decreases because inflow is constant. So this ratio will depend on value of capacity. So as capacity reduces, trap efficiency also reduces. So let us look at the solution. As I said before, the annual sediment inflow is 3000 tons, which is first converted into kilogram, then into volume by dividing it with density. Then there is initial reservoir capacity, that is 50 million meter cube. There is average inflow, that is 50 million meter cube again, and we find initial capacity inflow ratio, that is when the reservoir is at full percentage capacity, what is the capacity inflow ratio? 50 by 50, that is equal to 1. But the thing that we can understand here is the reservoir capacity is equal to average inflow. So whatever comes in, the reservoir is storing that. But that may not be the case every time. That sometimes average inflow can be less than initial reservoir capacity. Say the average inflow is 40, then initial capacity inflow ratio will be 50 by 40, that is 0.8. And this initial capacity inflow ratio goes on decreasing as sedimentation takes place. Why? Because capacity decreases as sedimentation takes place, and in turn trap efficiency decreases. And the volume that we have chosen here is a step of 20, that is we'll take it at 100% efficient, 100% capacity, 80% capacity, 60, 40 and 20. Again, even though in the procedure we have said 10%, you can take it as 20 for ease of calculation during exams and while you do in your notebooks. And another relation that we have to remember is trap efficiency is equal to sediment retained by total sediment. What sediment is retained and what sediment is coming to the reservoir. The ratio between that is trap efficiency, which is represented by eta. And volume interval chosen is, as I said, 20%, that is 20% of initial volume, 50 into 0.2, 10 million meter cube. So let us now look at the table and for calculating the useful life, that is the years that it will take before it is filled 80% with sediments. As I said, we are taking steps of 20, 160, 180, 60, 40, 10 and the volume change following it, that is 100% is 50, 100% of initial volume is 50, 80% of initial volume is 40. And what does this interval signify? It means as this starts, the full volume will be filled with water, and at this point 20% of it will be sediment and 80% of it will be water, and that's how it goes. Then we find capacity inflow ratio. Here inflow remains constant, so with decreasing capacity inflow ratio also decreases. Then we find trap efficiency corresponding to the capacity inflow ratio from the table given. And then for this interval, this trap efficiency is at 100% capacity. This 0.97 trap efficiency is at 80% capacity. So for this interval 100 to 80, the trap efficiency will be average of this value. Similarly, average is found for all the other intervals. Then in order to find, then we find what annual sediment is trapped. The annual sediment that comes to it is 0.24 million meter cube, and for the first interval 0.9735, that is 0.24 into 0.9735 of it will be trapped in the reservoir. And for the second interval 0.24 is again coming, and 96.5% of that will be trapped in the reservoir. So the trapped sediment, as you can see here, is decreasing because, as I said before, with decreasing capacity, the deposition of sediment also decreases. So this gives the amount of sediment that gets deposited in 1 year. Here the interval that we have taken is 20%, that is 20% of initial capacity, which is 10 million meter cube. So to find the number of years, we have to divide 10 by the sediment that gets deposited in 1 year. So we obtain percentage, years that it takes to fill 20% with sediments, another 20 over here, and then we add all of this to find the life of the reservoir. That's it. Thank you, friends.
Reservoir Sedimentation Control. Reservoir sedimentation control can be controlled by two methods, that is by pre-construction method and post-construction method. In pre-construction method, there are three ways to control the sedimentation, that is by the selection of reservoir site, by reservoir design, and by the control of sediment flow. In post-construction method, it can be controlled by control of sediment deposition, by the removal of sediment deposit, erosion controlling catchment area. Pre-construction method is a method which is done to remove the sedimentation before the construction of a reservoir. Here, selection of reservoir site. We know that reservoir sedimentation can be controlled by choosing a site in such a way that where the sediment inflow is low. The site which excludes the runoff from an easily erodible part of the catchment area is more preferred for this. It can also be done by control of sediment inflow. For this, constructing check dams and by providing vegetation screens can be done. Check dams are the dams which are built across channels or gullies to reduce the rate of intensive flow, monitor and trap sediments which are of large coarser materials, and to reduce the flood discharge. Now coming to the reservoir design. The rate of sedimentation on a small dam constructed near a river with large inflow is found to be less as compared to large reservoirs. That is, uh, that is when a large reservoir is constructed near a river which has high inflow. Therefore, the sedimentation rate will also be high. So that a small dam which is constructed near a river with a large inflow is preferred over this one. Now, so the sedimentation can be also be controlled if the initial height of the dam is lowered, but provision should be taken to raise the height of after some years so that the capacity can be increased. We can also provide adequate number of outlets to let the flooded water out. Now coming to post-construction method. These are the methods which are used to remove the sediments after the construction of the reservoir, and they are control of sediment deposition. Outlets should be designed in such a way that the water having high sediment content should be discharged to the downstream through outlets. So as we know that the sediment rates in a reservoir increases as the flooded water enters into it. So if outlets are provided to let the flooded water out, the sediment rate can also be decreased. After the deposition of the sediments in the reservoir, it can be removed by either by excavating or by dredging. It can also be done through scoring through the sluices. For scoring through the sluices should be provided at the bottom of the dam. But this brings a lot of structural problems. Hence, is not suitable. Hence, it is not suitable or preferred for the larger reservoirs. And also erosion control in the catchment area. So we know that erosion results in a lot of sediment deposition, so that if the erosion is controlled in the catchment area, the sediment inflow can also be controlled. So this erosion can be controlled by various methods that we have studied in our previous semesters, such as afforestation, control of grazing, providing check dams in gully form. So these are the methods to uh, control the sedimentation. So hope you all understood the presentation, and thank you for watching.